skewing towards the back. Makes lecturing very awkward. Who's ready for spring break? So now. We're gonna get through this, and then some of you might have something else today, but I don't. So I brought candy for those of you that were brave enough to come today on this last day before spring break. Help yourself and stuff. So I learned an important lesson. So I neglected to stop playing the music over my podcast, and so I went to upload that video to YouTube, and it immediately was like Apple Corp, who is the Beatles company. They were like, has blocked your video globally. And I was like, wow, Apple Corp, that was really fast. But I mean, I was playing like copyrighted material, right? So I got to be careful about making sure I don't include that in YouTube video, because apparently that process has become very efficient. Okay, so let's see. We're gonna basically today's gonna be pretty light, and then we're gonna hit it pretty hard when we get back. So we're gonna go through we're gonna do an entire chapter in a day today. I have no idea why the book splits alkenes into chapter 5 and chapter 6, but they do, and so we've already done even some of the stuff in chapter 5. So we're gonna see basically our goal is to wrap up chapter 4. And then wrap up chapter 5 today as well. And then as soon as we get that done, we'll get out of here. So to help us on some timing, I was a little ahead in the 10 o'clock section. And so we left off last time. Let's see, what did we say last time? So we said that we just left off that RNS does not correlate with laboratory or exploratory. And so we also want to include the idea of, well, sometimes we'll have what is called a racemic mixture. And so in a racemic mixture, basically we've got a 50-50 mix of both enantiomers, right? And so if we've got a 50-50 mix of both enantiomers, do you think that's going to rotate polarized light? Well, 50% of it's going to rotate it, plus way, and then the other 50% is going to rotate it the negative way. And so what's ultimately going to be the rotation? It's going to be 0. And so what we can say is that a racemic mixture, a perfect racemic mixture is 50-50. We're not going to rotate optically, or are not going to be optically active. It's not going to rotate polarized light. Essentially, it's because they cancel out, right? We have some positive rotation, we have some negative rotation, but we don't have any overall rotation. By the way, the theme song today is Mr. Blue Sky. I love yellow, and it may not be blue outside, but man, it is blue in my heart. I am so excited. I had to do it anyway. All right, so what we could have S2 iodobutane, and so in a perfectly pure sample of S2 iodobutane, we've got rotation of plus 15.9 degrees, and then if we have the other enantiomer, which is R2 iodobutane, you can see it's the same absolute value, it's just the other direction, and so we've got minus 15.9, and then ultimately if we have these two mixed together as a mixture that's 50-50, we have a racemic mixture, and so it wouldn't be optically active and we wouldn't see any light rotation. We'll do things like that in lab as we go. Okay, so to conclude, things that are not optically active and will not rotate polarized light. So anything that's achiral is not going to rotate polarized light. So if a molecule does not have an enantiomer, will it rotate polarized light? It will not, because all chiral molecules must have an enantiomer. And so the meso molecule, all right, so let's ask ourselves some more questions. A meso compound, does it have chiral centers? It does have chiral centers. Is the molecule chiral overall? It is not. So does a meso molecule have an enantiomer? No. And so is it going to be optically active? No. It's going to be a meso compound is achiral despite having chiral centers, and that's because of what we saw last class. Basically, it is achiral overall. So meso compounds are not optically active. And then, as we just went over, racemic mixtures are not going to be optically active as well. All right, so we'll do a little more with this to wrap up chapter 4. We're even writing in blue today for the anticipation of spring break. And so, let's see. What we wanted to find, so there's this idea of percent optical purity. So we'll do a little bit of this in lab. And so ultimately, it's a way for us to keep track of how pure things are. So we're going to have an observed rotation of some given sample. And so what we're going to do is we're going to compare that to the observed rotation of a pure enantiomer, and since it's a percentage, we'll then multiply by 100%. Okay, so what that does is that gives us an idea of basically how enantiomerically pure our substance is. All right, so for example, let's see if we have a sample. All right, so we have a sample with an observed rotation of 30 degrees. And we already know that the pure R enantiomer has an observed rotation of 75 degrees. Okay, so if we want to just figure out the optical purity, we can plug those numbers in, and so we end up with plus 30%, or degrees, sorry. Plus 30 degrees over plus 75 degrees times 100%, and so in describing the optical purity of our sample, we'd say that it is 40%. All right, so there's two ways that you'll see basically enantiopurity referred to. You're going to have percent optical purity. You're also going to see what's referred to as enantiomeric excess. And so this is typically what's used if you're developing organic reactions and you obtain a molecule that's able to make an enantiomerically pure compound. We're going to figure out how good it is, right? If it makes 90% R versus 10% S, that's better than racemic, and so we describe it using enantiomeric excess. And so what enantiomeric excess is, it's simply going to be the percent R minus the percent S, or you could go the other way. You could say percent S minus percent R. Depends on which enantiomer you're talking about. Importantly, whenever we talk about these two things, percent optical purity as well as enantiomeric excess, they're the same thing. They're equal to the same thing. So we want to add that percent optical purity is equal to enantiomeric excess. So what we can do now is we can take the information from above and basically figure out the composition of our mixture. So let's see. This up here, this should be 40%. There we go. All right, so it's going to be 40%, not 40 degrees. That wouldn't make much sense. All right, so from above, we had 40%. And so what that tells us is it's going to be 40% R. And we know that because, well, we're going based off of the R enantiomer that has 75. Now, if 40% is R, what's the other 60% going to be? All right, so everyone's going to say S. So let's think about if that makes sense. So if the pure R enantiomer rotates at plus 75, what will the S enantiomer rotate at? Negative 75. And so if our sample has a positive rotation, would it make sense for there to be more S than R? It wouldn't, right? Since we're seeing positive rotation, we would expect there to be more of the R enantiomer. And so that's exactly what it is. Instead of saying that the other 60% is S, the other 60% is racemic. And so ultimately that's 30% R and 30% S. And so our composition of our compound is, or at least our sample, is ultimately going to be 70% R and 30% S. And so that makes a lot more sense to see positive rotation like we see the R enantiomer. We should have more of the R enantiomer, and so that's what we actually see here. All right, this is getting dangerously close to math, so let's see if we can get away from that. So finally, so to wrap up this chapter, we'll talk about number 8 here, and so that's going to be the separation of enantiomers, which is not the easiest thing in the world. So separation of enantiomers, you'll also see this described as the resolution of enantiomers. And ultimately, so when you were making your crystals in preparation of lab 7 after spring break, that's basically what that lab is we're going through the process of how we would go about separating enantiomers. But it's not easy. All right, so enantiomers. When we talk about their physical properties, if we have a pair of enantiomers, a special pair, do they have physical properties that are the same or are they different? If the R enantiomer boils at 40 degrees, what's the S enantiomer going to boil at? 40 degrees. They have the same physical properties. And so that's an issue when we try to separate them, right? Because things that we've talked about, at least separation methods we've talked about in the lab, we've got things like distillation, but they're going to boil at the same temperature, so that's no good. They have the same polarity, and so using chromatography like our GC, if we put on a racemic mixture into our gas chromatograph that we've been using, do you think we'd see one peak or two peaks? We see one peak because they have the same polarity, the same boiling point. They're more or less identical except for their handedness. And so that comes, when we talk about the separation of enantiomers, it is not particularly easier. But diastereomers, do they have the same or different physical properties? Those are different. And so that is important, and it's going to allow us basically a strategy to separate enantiomers. So these have different physical properties. And that's because they are not mirror images of each other, right? They have bonds that are actually in different orientations relative to each other. And so because of that, they're going to have different polarities, which gives them different boiling points and melting points and things. So diastereomers are pretty easily separable, but enantiomers are, they're not. All right, so for example, the way that this is typically on bound, the way that we'll do it in lab is if you're given a racemic mixture of a chiral acid. And so we're going to have a racemic mixture of the R and S forms of our acid. Well, let's think about what we've got in our flask. So we're going to have the R acid, and we're going to have the S acid. And so the relationship between those two things, there's one chiral center in each, and they are opposite of each other. So are those enantiomers or diastereomers? So they're certainly enantiomers. So because they're enantiomers, they are not easily separable. But what we can do is basically we can take our racemic mixture and we can react it with something that is chirally pure, right? It is enantiomerically pure. And there's plenty of things that we can obtain enantiomerically pure that are pretty cheap. You can buy the one-handed form of amino acids. You can go online and buy 100 grams, and it might run you $30. So we can obtain these enantiomerically pure compounds with which we can react with our racemic mixture. And so what we'll do is we'll react our R and S acid with just an R base, all right? And so how many products are we going to form? We should form two products, right? So the first product is going to be RR acid-base salt, and the other product is going to be SR acid-base salt. And so the relationship between those two things, are they enantiomers or are they diastereomers? They're diastereomers now. They're not complete opposites. They don't have the opposite handedness. And so now what we've got are diastereomers. Diastereomers. And so those are separable. And so what we'll do now that we've got diastereomers is we can use techniques like chromatography or really a lot of different separation techniques to now separate these two diastereomers apart. Now we've got one in one class, one in the other. We can just cleave off that initially chirally pure base, and so what we've got now is the pure enantiomers that we were trying to obtain in the beginning. So that's typically how it's done. So in the real world, we say that they are not physically, or at least on paper, we can say they're not physically separable. In reality, there have been some technologies that have been developed, and so, for example, when we talk about chromatography, in our GC we use basically polarity to separate things, but it's an achiral environment. It's just polar, right? And so since enantiomers have the same polarity, it's not separable. But what's been developed are different forms of chromatography that basically use carbohydrates or sugars as the phase that is in the column, right? And so the enantiomers are going to react with these chiral columns a little differently. And it's not the most efficient process in the world, and so often you can only separate a few milligrams at a time. But it is, so there have been ways that have basically been developed to separate enantiomers, but it's not efficient, and if you've got 100 grams of something, of a racemic mixture, and you want to separate them, it's probably not going to work. You're not going to get the separation that you need. So, there are other technologies, and there's things in addition to that people have developed, but it's a really tough problem. I mean, we had one in the lab that I worked at in Michigan, and so one of these, chiral GC columns, the column itself can run you $10,000. And then the entire system, I mean, you can easily spend $100,000 just on something that can separate a few MIGs of material, right? So it's a challenge ongoing. Okay, that's it. That's chapter 3. So, yay. We're literally going to do chapter 5 in like 35 minutes. So, thought there'd be more yays. Yay. All right. If someone needs sugar, just come down and grab you something. I don't know. Okay. So chapter 5, like I said, I have no idea why they separate alkenes into 2 different chapters, but they do. And so we're going to hit the chapter 5 stuff today. So chapter 5 alkenes, and so we've honestly done a lot of this information already. So some of it will be review, and some of it we will forge ahead. Just seriously get candy. I don't care. All right, so chapter 5 alkenes. Let's relate this stuff to the real world. It's always fun. And so we're going to do an intro section. I think we're only going to have like 2 Roman numerals this entire chapter. So Roman numeral 1 is just intro. And so we're going to take a few minutes and we're going to talk about fatty acids. All right, so fatty acids are certainly everywhere. They're important medicinally. They're important biologically for like cell membranes and all sorts of things like that. So when we talk about our food, we typically talk about 2 kinds of fatty acids. What are those? Saturated and unsaturated, right? So we've heard both of those things. So we're going to talk about 2 forms. We're going to talk about saturated, and we're going to talk about unsaturated. All right, and so as an example of that, a saturated fat, we'll use palmitic acid. And so palmitic acid has 16 carbons in it. And so this is pretty standard. This is pretty typical of what a fatty acid looks like. So you're going to have 16 carbons. That's 6, 8, 10, 12, 14, 16. And at the end, you're going to have a really polar group. And so we call that a saturated fat because this alkane part, right, it is saturated. We can't put any more hydrogens on there. There are as many hydrogens that can go on those carbons as is possible right there. Alternatively, we can have unsaturated fats. And so what do you think is going to, what's going to be the difference, you think, from a saturated to an unsaturated fat? We're going to have a double bond, right? I mean, it makes sense. We're in chapter 5 now. So what that's going to look like is an example, again, with 16 carbons, I hope. Let's see. 8. I don't know. Close enough on carbons. All right, so what we end up having is now we have a double bond in there. And so what we can say about this chain versus this chain is that, well, there are as many hydrogens as possible in here, but that's not the case here because we could potentially add 2 more hydrogens to our double bond to basically form our saturated fat. We're going to see that we try to do that, but we often have some unintended consequences when we do so that can be pretty important on a pretty big scale nutritionally. Okay, so the sources of saturated versus unsaturated fat. Typically, saturated fats are going to be coming from animals, whereas unsaturated fats are going to come from fish and plants. And so typically, we think of unsaturated fats as being a little healthier than saturated fats, right? One big difference physically between these 2 things is that the melting point of palmitic acid, like I said, that's C16, so palmitic acid. It's going to be around 63 degrees Celsius, which at room temperature, is that going to make that a solid or a liquid? It should be a solid. And then the unsaturated fat example is going to melt around 13 degrees Celsius. So is that solid or liquid? That is liquid. And so while unsaturated fats are they're typically healthier, they're a little tougher to package and deliver because it's a liquid, right? It could leak. You have to spend more money to basically get this into people's refrigerators. And so what people will do, or at least what we've done for a long time, is we'll take this unsaturated fat and we'll basically try to hydrogenate it. Meaning we're going to try to just have lots and lots of hydrogens. We're just going to flood it with hydrogen and hopefully get it fully saturated. And the idea of this hydrogenated fat is that we're going to essentially raise the melting point such that it is now a solid and it's cheaper for us to deliver to people. So what we create are hydrogenated fats, which you've probably heard of as not being particularly good health-wise. And so we can talk about why that's the case. So hydrogenated fats are the product from the hydrogenation of unsaturated fats. And so the pros to that is we have, it's more stable, so we have longer shelf life. We don't have to throw as much away if we don't sell it in the supermarket, so longer shelf life. And that is ultimately because it is a solid. Now, some of these fatty acids, I've shown an unsaturated fatty acid with one double bond. So notice that the linkage in this double bond, is it cis or trans here? It is cis, right? And so that's going to be important. All right, so sometimes in unsaturated fats, we don't just have one double bond. We could have multiple double bonds. We could have a number of them. And so when we hydrogenate things, let's see, kind of drawing this on a whim. What we could have are structures that look like this. Probably not going to have that there. Let's put that there. All right, so we've got double bond, double bond, double bond, double bond. So we're going to hit this thing with basically hydrogen, and we're going to see if we can't convert all of those double bonds to single bonds. And so we undergo hydrogenation. Let's see, how many carbons we got? 2, 4, 6, 8, 10, 12, 14. All right, so we've got 16 there. And so what we'll see is some of them are, in fact, they're converted to the single bond. So we have our saturated fat, and I guess that's the goal, even though we know that's a little unhealthier. So 2, 4, 6. But sometimes we don't have the conversion that we're looking for. And in fact, what happens is one of these cis double bonds gets converted to a trans double bond. We try to hydrogenate it, but in fact, all we do is we isomerize it from the cis version to the trans version. So now we've got 2, 4, 6, 8, 10, 12, 14, 16. Okay. And so now we kind of have this kink in our fatty acid, right? And so it's going to exist differently in space. And so the cons, when we talk about hydrogenated fats, is, so what is the fats that, I'd say over the last 10 years have been determined to be really, really bad for you? Trans fats. And so that's why these things are called trans fats. It's because ultimately we're trying to make the shelf life better of our unsaturated fats by basically saturating some of the double bonds. And we're successful to a large degree, but it's not a perfect process. And so we end up with trans double bonds here. And so when we have a trans double bond, those things have certainly been linked to heart disease and high cholesterol. Kind of a double whammy. So even though these double bonds, cis versus trans, might seem to be relatively innocuous, it can have a pretty big effect considering that we've got billions of people on the planet that are eating more of these hydrogenated fats. And ultimately, billions of people, we're going to have a large portion of people that are going to suffer because of that. So just a little introduction to alkenes as they are important in the real world. All right, so now we'll just do a little bit of review about what a lot of this you've seen. We've really already done it. So when we draw a double bond, what we can draw is if we put our trigonal plane in the plane of the board, where do our p orbitals live? Perpendicular, right? And so if we have our trigonal plane in the plane of the board, perpendicular would be depth. And so how do we draw depth? So when we draw p orbitals, how do we draw depth? We draw it on a diagonal, right? All right, so we can draw it on a diagonal, or we can put our trigonal plane as having depth. And so in that case, what direction will our p orbitals go? Yeah, so now our trigonal plane is basically like this sheet of paper, and so perpendicular is going to be straight up and down, and so it's in that case that we can draw this just on the y-axis, like that. All right, so that's going to be important when we start talking about reactions on the Monday after spring break, but right now, just a little bit of review, and then furthermore, I know I said this a a billion times, but we'll say it one more time. There's going to be no bond rotation in double bonds because it takes a ton of energy to basically break the double bond, and so at room temperature, it's just not something that happens. So if we have a cis double bond at room temperature, it's just going to stay as a cis double bond. When they try to hydrogenate the cis fatty acids and they make trans fatty acids, typically, so they're going to have high pressures of hydrogen, they're going to have a metal catalyst in there, and they're probably going to heat it up a lot. So they basically have to use a catalyst, and they have to heat to a high temperature to ever make that isomerize into the other double bond. All right, so we've talked about cis versus trans. Let's think about which would be more stable. So if we had a trans double bond, that looks like this. All right, so how would we name this? First off, what's the longest carbon chain? Should be 4, right? We could number 1, 2, 3, 4. So there's a carbon chain of 4. If it's 4, what's our root name going to be? Bute. So it's got a double bond. So we don't say butane, we say butene. And then furthermore, we have to indicate a location of our double bond. So what carbon, basically, as we count, do we first approach our double bond? 2. And so we'd say this is basically 2. butene. We don't have to say 2, 3. It's always assumed that the double bond continues in what direction that we're numbering. So we don't have to add basically extra information that doesn't actually provide anything. And then furthermore, is this cis or trans? This is trans, and so we want to make sure that we said trans 2-butene, like that. Alternatively, we can have the cis form. So in that case, we're going to have our methyl groups on the same side. It's a very similar name. We just change the trans to cis. We might ask ourselves, well, which is more stable? Is it going to be the trans 2-butene or the cis 2-butene? I think I hear both. And so what we want to do is we want to think about strains. So we're going to have possibilities for steric strain. And so the big difference is that in one case, we've got methyls on opposite sides of the double bond. And the other, we've got the methyls on the same side. So which are more likely basically to clash into each other and have some steric strain? Definitely the cis. And so what's going to be the most stable? Trans. So that's in general what we see. So in general, trans double bonds. I'm going to start saying DB for double bonds. So trans double bonds, more stable than cis double bonds. So again, that's just basically steric clash between the methyl groups that are on the same side when we have the cis. So we would say we have steric strain right there. All right, so let's see. We got to do a little nomenclature, and then that's going to be pretty close to being done. So this will just be our second of 2 Roman numerals for chapter 5. We'll say there's nomenclature. And so some of these rules we already know. So for example, rule 1, instead of ending it as hexane, if it had a double bond, we call it what? Hexene. And so we have a double bond, so this is nomenclature of double bonds. We're always going to make sure we end in -ene. So I think we, for the most part, know that. What we also want to say is that our double bond, let's see, I don't want to say that. Yeah, but we also know this rule. So the double bond is basically named or located using the number of its first carbon. And so that's why up here we called that just 2-butene. We didn't say it's 2,3-butene. We didn't say it was 3-butene. It's just 2-butene. It's the first carbon in that double bond that we get to when we count. All right, so that stuff I think we pretty much already know. Here's a new rule. So what we have to do when we number is we have to come up with a numbering system that must, absolutely must, give the double bond the lowest possible number. All right, so what that means is we, for example, we could have a molecule that looks like this. Okay, and so there's let's see, change this a little bit. All right, so we use that. So we've got two possible ways to number. We could number left to right, 1, 2, 3, 4, 5, or we could number right to left, 1, 2, 3, 4, 5. Now, in our previous rules that we've learned, we would look at this and we'd say, okay, so if we number left to right, we hit a bromine at carbon number 1, and so that's probably what we want to do. But our new rule, whenever we have alkenes or double bonds, is that the numbering must give the double bond the lowest possible number. And so as we look at the first carbon we would approach, we see that in the red numbering system, it would be carbon 3. In the green numbering system, it would be carbon number 2. And so do we use red or green? Okay, we definitely use number green, color green, so that we give that 2 basically to the double bond. All right, so what's our longest carbon chain here? It's 5, and so we're going to say that that is a 2-pentene. And then we have one substituent, and so that is going to be a 1, sorry, because we use the green numbering system, we say it is a 5-bromo. And so ultimately, when we name this thing, we'd say that it is 5-bromo 2-pentene. But we're not totally done, because do we have stereochemistry anywhere in this molecule? What about the double bond? It could be cis or trans. What is it in this case? It's trans, and so we want to make sure that we indicate that by saying trans. Or you could use EZ nomenclature. Would you use E or Z? Yep, so you could also call it E 5-bromo 2-pentane, or pentene. And so furthermore, if you're going to use the EZ naming or the RS, you want to just put those in parentheses like that. We'll have another example or two of that as we go. All right. Another new rule as it comes to alkene nomenclature is that the parent chain must include the double bond. So for example, we could have this structure. And so what is just the overall longest carbon chain? Well, we should count 1, 2, 3, 4, 5, 6, 7, 8, 9, right? So we've got a carbon 9. But does that include the double bond? It doesn't. So what we're going to make sure we do if we count using a molecule with an alkene, we want to make sure we're including this as part of the chain. So we could say 1, 2, 3, 4, 5, 6, 7, 8. So in reality, you're going to say that our group name could be 8 carbons long, because the parent chain has to include a double bond. Furthermore, are we going to number left to right or right to left? Definitely left to right, because we want that double bond to have the number 1 instead of the number 7. All right, so we'd say 1, 2, 3, 4, 5, 6, 7, 8. All right, so it's 8, so we'd say we've got 1 octane. And we've got a substituent now that is a 3-propyl. What about stereochemistry in this molecule? So if we just look at the double bond, do we ever have stereochemistry in a terminal double bond? No, because we basically have 2 hydrogens coming off of here. There's no way to prioritize. This would be a chiral center, but I haven't drawn any stereochemistry, and so you can just assume it's a racemic mixture, so you couldn't name that because you don't know basically if the hydrogen here is a wedge or a dash. So we'll just say that this is 3-propyl, 1 octene. You really don't have enough information to say anything about the stereochemistry. You can't name the double bond stereochemistry if you don't know the stereo center. All right. So then we're going to learn a couple of rules about cycloalkenes. So rule number 5 is going to be that the double bond always gets the numbers 1 and 2 in cycloalkenes. And then the other rule we'll learn is that we always number in the direction of the first substituent. So we've sort of seen that rule already. All right, so we'll learn it through examples as we've been doing all along. So one example we could have is going to be this molecule. All right, so rule number 5 says that we must give the double bond number 1 and number 2. So now what we've got to decide is, are we going to number this thing clockwise or counterclockwise? All right, so we have two possibilities. We could say that the top carbon is carbon number 1, and number this way, or we could say that this carbon is number 1, and we number this way. All right, so in both cases, all right, so we've got two methyl groups. In both cases, we're going to have a methyl off of that double bond. And so if we count 1, 2, 3 using our red system, we're going to end up hitting the methyl on carbon number 1. If we go the other way and we say 1, 2, 3, well, now we're hitting that methyl on carbon number 2. And so we're going to use red or green. We're definitely going to use red because that's where we give our first encountered substituent the lower number. So we definitely use red. So in this case, what we have is, let's see, 1, 3 dimethyl 1 cyclohexene. Is it going to be necessary to say 1 cyclohexene? No, because we say in the rules that we always give carbon number 1 to a double bond, and so you could say just cyclohexene, and that would be perfectly fine. Yeah.
So we're looking at several double bond.
So it's only in basically it's only in cyclo. So we do two things when we have a cyclo out. First, we know that we want to give double bonds 1 and 2, but we go either way, right? And so the way that we go is just going to be we want to get the first priority or the first encounter substituent the lower. And so since we get a methyl on number 1 here versus the methyl on number 2 going the other way, we want to use it where it's on. Yeah.
What did you say we can disregard?
I'm not sure.
Okay. Like, do we have to have that one there? Is that?
Yep, so, oh yeah, no, yeah, I understand what you're saying now. So this one right here, you don't have to include because it's assumed that, we say by rule that 1 and 2 are always a double bond. So you know, without seeing the 1 here, that the double bond is basically between carbons 1 and 2. Yep. All right, so another example. All right, so we have this. So we know that we must give the double bond 1 and 2. So we can do one of two things. We can say 1, 2, 3, 4, 5, 6. Or we number 1, 2, 3, 4, 5, 6. And so what we learned when we talked about cycloalkanes is sometimes we're going to experience cases where we want to make sure that the sum of the substituents is low. But we don't have that rule here. Basically, again, if we name the green, or we use the red numbering system, we're going to hit our chlorine substituent on carbon number 2. If we use the green numbering system, we're going to hit it on number 1. So which do we use? Green, because it's lower. So even though we're going to end up with 1,6-dichloro, that's going to be what we do, right? Basically, we want to make sure that we're giving this chlorine the lowest number possible. So instead of 2,3-dichloro, we want to make sure we say 1,6. So this would be 1,6-dichloro cyclohexene. If you say 1-cyclohexene, that's fine. I don't mind information that is basically extra.
So adding the substitution itself to make the lowest number, that doesn't apply?
That doesn't apply with cycloalkenes, yeah. And it's because we have to, since we have to put 1 and 2 on the double bond, there's only 2 possibilities, and so we just pick the 1. It's an easier rule, basically. Okay. There are a few common names with double bonds, and so if we see this molecule, what is our longest carbon chain? 2, and so what's the root for 2? F, and so we'd say it's ethene, but you're never, ever, ever going to see this called ethene. And so what people refer to this as is ethylene. I don't have the best explanation for why that is, but you're never going to see, if you call it ethene, that's perfectly fine. If you ever call something by the correct IUPAC nomenclature, that is fine by me. But just have a heads, it's like when you see isopropyl alcohol in the store. If you were buying ethene, it would be ethylene. It's just what people call it. All right, so furthermore, we have some substituents that have common names. So this is referred to as a vinyl group. And so you've probably all heard of PVC pipe. So what does PVC stand for? All right, so first off, so PVC pipe is a polymer. What's a polymer? Yeah, so polymer is basically kind of like a chain. So you have monomers, right? So you have a monomer A, and so you have repeating units, and you can have this thing that's hundreds or thousands of units long. And so ultimately what happens is they get wrapped together and tangled up, and so that's how we make things like plastics. That's what we give plastics their special properties. They're huge, long chains. And so PVC pipe is made out of a polymer, and the way that we name our polymers is based on the monomer that we use to make it, right? So the individual chain links is how we name our big, long polymer. And so the monomer in PVC pipe is polyvinyl chloride, and so that's where the name PVC comes from. So basically we have a monomer that has a vinyl group on it, and so that's how we have our real world name of PVC pipe. Okay, another one looks like this, and that's referred to as an allyl group. All right, so just some common names. These are used more often than the IUPAC nomenclature would ever be used. All right, so close. So let's do a couple of examples of naming, and then we'll see if we can get out of here. So, our example we'll use here. All right, so what's our longest carbon chain in this case? Yeah, it's 3, and so we know we want a number to give the double bond the lowest number, so we've got 1, 2, 3, and so we'd say this is 1 propene. Do we have to say 1 propene? Could you ever have 2 propene? Yeah, because what you'd ultimately be looking at, you'd be looking at this versus this, and knowing that we always want a number to give the double bond the earliest numbers, ultimately those are the same thing, right? So we don't even have to say 1 propene, because there's only one kind of propene. And so we've got substituents, but we don't have 2 hydrogens here. Basically, we've got 3 big substituents that aren't hydrogens. So can we use cis-trans? We can't use cis-trans. And so what we've got to do is prioritize. So we know bromine is going to be higher priority than hydrogen. So what about between iodine and the methyl group? Definitely iodine, because we're just looking at atomic mass. So is that going to be E or Z?
Z.
Yeah, they're on the same side. The higher priority group's on the same side, and so we call that Z. All right, so our substituents now, we've got a 1 bromo, and we have a 2 iodo. And so if we want to name this thing, we put all the stereochemistry information up front. So we've got the letter Z, so we'd say we've got Z. I'm sorry, it's 2, yeah, no, that's good. All right, so we've got Z, 1 bromo, 2 iodo, and then we can just say propene because the 1 is unnecessary. Why does bromo come before iodo? It's just alphabetical, right? There's substituents, so if those were swapped, bromo would still come in front. It would just now be 2 bromo, 1 iodo. All right, let's do another one. Yeah, Alec?
Is this supposed to be a dash between the iodo?
Technically now, so there should be no dash there. Yeah. All right, so another molecule we could name. Let's see. I'm gonna draw this one out big. All right, so we've got out some stereochemistry information here. So first off, how many possible stereoisomers will there be of this molecule? So the first thing we do is we add up basically how many RS or EZ sites we have. So how many possible locations are we going to have to give some stereochemical information? Should be 3, right? So we've got 2 chiral centers, one here, and then we've got this Z double bond. And so that's a total of three basically stereochemical sites we have to name. So we say there's 2 to the 3 possible stereoisomers. So how many? There'd be 8. So there's 8 possible stereoisomers. So we absolutely have to make sure that we're giving the correct stereochemistry. So the first thing, we'll just work left to right. The first thing I would do is prioritize and figure out what the stereocenters are. So we know bromine is 1, hydrogen is 4. And then the CH2 connected to a carbon will definitely be higher priority than a CH3. And so when we do our thumb trick, let's see, if we use our right hand, so the thumb or the hydrogen's going back, so put your thumb backwards. Can we rotate 1, 2, 3? Yeah, we can. And so what's that stereocenter? It's R. And then alternatively, the other stereocenter we need to prioritize first. So we would say that we've got 1, 2. What's going to, or I'm sorry, 1 and 4. How do we distinguish 2 and 3? So we'll redraw it out. So basically what we've got is going to the bottom right. We've got a carbon connected to a carbon there. But how many and when we have a double bond, how many times do we assume basically this carbon is connected to the second carbon? Well, it's connected twice, and so how many carbons do we say it's connected to? We say 2. So we know one of the connections is the hydrogen, and so what we end up with is basically this sort of structure. So it's making a double bond, and we assume it's connected to 2 carbons. Going the other direction, we've got hydrogen, hydrogen, and carbon. And so what's going to be higher priority, the group on the left or the group on the right? Definitely the group on the right, because we've got a second carbon there. So we will number 2 and 3. And so finally, let's see, if we try with our right hand, our hydrogen's coming towards us, and we count 1, 3, 2 that way, so we're going to try the other hand. All right, so hydrogen towards us, and we could go 1, 2, 3. And so if it's my left hand, is that going to be R or S? It's going to be S. And then finally, we get to the double bond, and so would we give that E or Z? That is definitely E, because our groups are on the same side. Okay, so we've got our stereochemical information. So we have to number our carbons. Are we going to number left to right or right to left? So remembering our rule that we always want to give the double bond to the lowest number, it would be right to left. And so we'll say we've got 1, 2, 3, 4, 5, 6, 7. And so our root name we'll use is 2-heptene, because we're indicating that it's the 2 and 3 carbons that are double bonded. And so then, let's see, we've got a 4-chloro, but we know that that is an S-4-chloro. And then we've got an R6-bromo. Furthermore, this is E. All right, so how do we put all this information together? Basically what we're going to do is we're going to take all of our stereochemical information and just put that in front and separate it out. And so the way that we can keep track of what is basically we'll say parentheses 2E, 4S, 6R. And so basically we know each of the carbons that has stereochemistry, we know which one we're referring to when we use our R, our S, or our E. And so then we would just name as normal. So we'd say 6-bromo, since it comes first alphabetically, and then 4-chloro. And this time, do we have to say 2-heptene? Yeah, we do, because we could have 1-heptene or 3-heptene. So that's how we go about naming that. Any questions? Yeah.
How are there 3 stereocenters?
So there's not 3 stereocenters or chiral centers, right? So whenever we say, and basically, I've been asked this question a few times because it does come off very ambiguous. When we talk about a chiral center or a stereocenter, it's the same thing. And so basically, that's only going to be the cases where we're using R or S if we say stereocenter or chiral center. Kind of the center is the key word there. What you'll see, at least the book referred to, is when we say stereosite, then it's referring to double bonds as well. No, it should be E.
You just said it wrong.
Did I say it wrong?
Yeah, earlier. But
Oh, no, it should definitely be E. And so the way to remember that is on an E, on a letter E, everything's on the same side, and so of course on the double bond, that means they're on opposite sides. We're seeing. All right, have a good spring break. And by the way, I've noticed a trend. No one likes orange. I have so many orange Starburst in my office now. What's up? Yeah. Yep. And so I haven't put them up yet, but basically, over spring break, I'm going to work on putting stuff together. So I'll send out an email whenever I start getting things posted.
Oh, Dr. Mark, quick question.
Yep.
So for the last problem on the prioritizing,
Yep.
the chlorine would be 1, hydrogen would be 4. So this, I guess, would be 3. But if you follow that chain, doesn't it eventually reach a bromine?
But we look at the first point of difference.
Okay.
And so what we see is this carbon right here and this carbon right here. They do have different connectivity. At
Right.
that point.
Okay.
And so we just cut it off there.
Okay.
Yeah.
Thank you.
Yep.
Professor Ball, quick question. So when we have more than 2 main substituents, do we just look at the 2 biggest substituents to determine whether it's cis or trans, or E or Z?
You use the you just prioritize like we would do for a chiral center.
Okay.
And so in this case, we know bromine is bigger than hydrogen, and then iodine is bigger than carbon.
Okay.
So yeah.
And
So
then-
since they're on the same side, we call it a Z.
Okay. And then for this one, why couldn't we distinguish between cis or trans in this molecule?
Because ultimately what you've got is you've got a hydrogen here and a hydrogen there.
Yeah.
And so we don't know if they're on opposite, right? Basically the hydrogens don't allow us to distinguish one side or the other, and if we can't distinguish, we can't give it a name.
Okay, because we didn't have wedges and dashes. Or we
Yeah,
weren't
but
told.
you don't even need wedges and dashes. Basically, if you have 2 hydrogens coming off of 1 carbon in a double bond, basically if it's a terminal double bond,
Okay.
you just can't have stereochemistry.
Okay.
Yep.
What's up,
Hey,
everyone?
what's up?
Quick question for you, and I sent you a quick
Oh yeah,
email.
I saw that email. I just
the
didn't
other day.
respond to it. Yeah.
Oh, thanks.
Yeah.
Appreciate it. Right, so
I would take the book home anyway if
Yeah.
it's not too much hassle, because I might glance through it and see if there's any good problems in there.
Okay.
But my goal is to basically be book free in this class in the future.
okay,
I don't know if we're totally do that yet. So
because I don't know. I mean, if you assign, I guess I could just look through some of the
I certainly
problems and then-
I'm hoping to make the majority of questions
Okay.
not in the book.
But you will
So,
have some.
It's possible. I
Okay.
have no idea.
Okay, that's
that's why I didn't answer your email, because
Yeah.
I didn't know the
That's
answer
cool.
to the question.
And then when do you think you'll have those posted? Or?
I'm hoping to. Okay.
to put the